Acids and bases 4. Strengths of acids and bases. Essential ideas. The pH depends on the concentration of the solution. The strength of acids or bases depends on the extent to which they dissociate in aqueous solution. Nature of science. Improved instrumentation. The use of advanced analytical techniques has allowed the relative strength of different acids and bases to be quantified. Looking for trends and discrepancies. Patterns and anomalies in relative strengths of acids and bases can be explained at a molecular level. The outcomes of experiments or models may be used as further evidence for a claim. Data for a particular type of reaction supports the idea that weak acids exist in equilibrium. So, obviously there's a difference between a weak and strong acid. An obvious idea would be, it's fine to drink vinegar, but you would die instantly if you tried to drink battery acid. So there's obviously a difference between the two things. And it's all about dissociation. Strong acids and bases completely dissociate to become ions. In other words, they ionize. And you can see here that hydrochloric acid or sulfuric acid, when reacting with water, we're using an arrow, a single arrow, to make the hydronium ion and the chloride ion, or the hydronium ion and the sulfate ion. These reactions go to completion. The forward arrow is used. These molecules are fully dissociating into ions in solution. So these ions are present in solution and these molecules are not. Weak acids and bases partially dissociate. And you can see we show this, that we've got the molecules on this side, we've got the ions on this side, and with ethanoic acid, we're using the equilibrium arrow, arrows pointing both ways. So you're going to have the molecules existing in solution and the ions existing in solution. So, strong acids and bases. Let's have a look at 3 different ways to show how a strong acid behaves. The first we just looked at, we use the single arrow. These are going to completion. We are getting a solution that only contains the ions. No molecules remain in solution. Another way to think of it, if you've got an acid, HA, we could draw them like this. The molecules in solution look like this. They're bonded together. But in solution, the reality is there's full dissociation. You can see that no blue circle is bonded to a little white circle. They are free to move around as ions. And so the hydrogen ion is free to move around. And so there's a high concentration of hydrogen ions in solution. Another way to think of it would be if you were to draw a table. It's not a table, is it? It's a graph, a bar graph showing how the initial molecule dissociates into the ions. You can see that we get full dissociation in the final state. There's no HA there. We'll put a little H there to show you where it wouldn't be. You need to memorize these. The big 6 strong acids, you've got hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid. So commit those to your big brains. And we need to also remember the big 4 strong bases. You've got lithium hydroxide, sodium hydroxide, and potassium hydroxide, and barium hydroxide. Weak acids and bases. There are good ways to show this, the 3 same ways. Obviously, we can use the equilibrium arrows pointing both ways, showing that you've got some molecules and some ions in solution at the same time. And so if we look over here at the final state of a solution, you can see we've got some molecules and also separate ions in solution. Here you'd have some molecules, mainly molecules, and you've got some of the ions. So you've got some hydrogen ions free there to act as an acid, or these would be acting as a base. If it's not one of the big 6 strong acids we looked at before, it could be one of several weak acids. We've got organic acids, the carboxylic acids, such as ethanoic acid. We've got several others here. We've got carbonic acid, phosphoric acid, sulfurous acid. Notice a little 3 there, it's not a 4. Hydrogen cyanide. And for high level folk, many transition metal solutions with hydrated metal cations. If it's not one of the 4 big strong bases, then it's going to be a weak base. We've got ammonia and hydrazine. We've got the organic bases, amine groups, and some anions that are the conjugate bases of weak acids, such as ethanoic, etc. So, strength of acids and their conjugate bases. Let's have a think about this. If an acid is strong, then its conjugate base is weak. Conversely, if an acid is weak, then its conjugate base is strong. And this will make sense. A strong acid very willingly gives up its proton. So this very willingly gives it up. Yeah, oops. This acid very willingly gives up its proton. The reaction goes completely to the products. So we're getting just these existing in solution. If the conjugate base here accepts an A plus to reform this acid, then the acid will just dissociate straight back this way. So this does not hold on to the H plus, making it a very weak base. Down here, we've got a very weak acid, and it doesn't willingly give up its H plus. There's a strong tendency for the conjugate base A minus to accept an A plus, to accept this H plus back, to reform the acid, making the conjugate base stronger, or relatively stronger base, compared to a conjugate base or a strong acid. Okay, let's do an example. Identify the conjugate base of each acid in the pairs below. Circle species which is a stronger conjugate base. Let's read there. Have a think about that. Just pause. Okay. So we want to identify the conjugate base of each acid in the pairs below and circle the species which is a stronger conjugate base. So we know that the weaker acid makes the stronger conjugate base, and ethanoic acid is weaker than nitric acid. This is one of the strong acids. Okay, so the conjugate base of this ethanoic ion is a stronger conjugate base. Down here, HBr and HF. HBr is one of the strong acids, so we know that it will have a weaker conjugate base. So HF has a stronger conjugate base. Down here, NH4 plus and HCl. Once again, we know HCl is one of the strong acids, so it is going to have a weaker conjugate base. This is a weaker acid, so it's going to have a stronger conjugate base. Strength of bases and their conjugate acids. If a base is strong, then its conjugate acid is weak. If a base is weak, then its conjugate acid is strong. Up here, a strong base has a very strong attraction for the H plus. It wants this H plus. The reaction goes completely to the products, and then the conjugate base, H plus, does not readily donate the H plus back to the A minus. So this is a weak acid. It's not going to readily give this up to the A minus. If a base is weak, then its conjugate acid is strong. A weak base has a weak attraction for H plus, and so this is not strongly attracting this. When the conjugate acid BH plus forms, it will readily donate the H plus ion to the base. This makes the conjugate acid relatively stronger acid. It will happily give up that H plus. Another example, identify the conjugate acid of each base in the pairs below, circle the species which is a stronger conjugate acid. Have a think. Okay, well, we know whichever one of these is the weaker base will have the stronger conjugate acid, and KOH is one of the strong bases, so ammonia will have a stronger conjugate acid of these two. If you look back, you can see the barium hydroxide is one of the strong bases, so it's going to have a weaker conjugate acid. So this weak base will have a strong conjugate acid. C, this is HL only, but you can see straight away we've got ethanoate and bromide ion, and their conjugate acids are going to be, just add an H plus, we're going to get ethanoic acid, and we're going to get hydrogen bromide. We know that hydrogen bromide or bromic acid is one of the strong acids, so this, the conjugate acid of this will be stronger. The differences in properties of strong versus weak acids. Consider the reaction of equimolar solutions of a strong acid and a weak acid. Let's first look at the rate of reaction with carbonates. The rates depending on the concentration of hydrogen ions. In strong acids, it's far faster and more vigorous. With weak acids, it's slow. What about the rate of reaction with metals? Again, depends on the concentration of hydrogen ions. Strong acids have a higher concentration of hydrogen ions, faster, more vigorous, and yes, you guessed it, it'll be slower and less vigorous. In weak acids, the rate of reaction with metal oxides, faster, more vigorous, I think you're getting the idea here, slower, less vigorous than weak acids. What about electrical conductivity? Remember, electrical conductivity depends on how many free ions you have in solution. Strong acids obviously have more free ions in solution, and so they're going to have a higher conductivity than the weak acids, where they're mostly existing as non-charged particles, as molecules. And the pH is going to be far lower because you've got a higher concentration of hydrogen ions in strong acids, and it's higher in you got a higher pH with weak acids, near 7. Another example 3. Have a read through these two. Press pause, have a read through, and see what answers you get. Okay, example 3. We've got which statements are correct. The weak acid is less dissociated than the strong acid. This, of course, is true. Strong acids fully dissociate. The strong acid reacts with a metal oxide, but the weak acid does not. It's incorrect. Just the strong acid will react more vigorously. 3. The strong acid has a greater conductivity than the weak acid. Well, strong acids do dissociate more, which means they've got more free ions, which means they'll have a greater conductivity than the weak acid. So 1 and 3 are correct. Example 4. 2 samples of 2 grams of calcium carbonate. We have got 10 centimeter cubed of either acid P or acid Q. Obviously P and Q are going to be one strong acid and one weak acid. Suggest giving a reason, a possible identity for acid P and Q. Well, you can see straight away that Q has a greater rate of reaction. You're getting, and the carbon dioxide is being given off far quicker than with P. So just think of any kind of strong acid. So let's just say HCl. And if I have a weaker acid, why not just go for ethanoic acid? Okay. Often people get confused between the strength of an acid and the concentration of an acid. Strength and concentration don't mean the same thing. If you have a strong acid, remember that just means that it fully dissociates. Okay, it's fully dissociating. So you can see here that you don't have any molecules present in this here. When it's strong, when it's concentrated, it's still fully dissociated, but you could have a dilute strong acid and you can see all of the acid is fully dissociated, no molecules are present. Conversely, you can have a weak acid here that's very concentrated. You can see there's molecules in the solution. Okay, many molecules in the solution, and there's a few ions, and that's concentrated. Or you could have a dilute weak acid. In the dilute weak acid, you still have some molecules there and some free ions. Example 5. Acid A is a weak acid. Acid B is a strong acid. Which of the following statements are correct about these acids? Have a think about it. Okay, A. The extent of dissociation of acid A is less than B. A is a weak acid, so it will dissociate less. If both acids are equimolar, the pH of acid A is lower than the pH of acid B. That's incorrect. B is a strong acid, so it's going to have a lower pH. It's a stronger acid. Concentrated solutions of acid A could have a higher concentration of hydrogen ions than dilute solutions of acid B. And that's true. You could have a concentrated solution of acid A where there's hardly any dissociation, so you've got very little, you've got a very low concentration of hydrogen ions in solution, and a dilute solution of acid B where only the ions are present. There's no molecules present. D, a very dilute solution of acid A is less corrosive than a concentrated solution of acid B. Well, of course that's true, because acid A is indeed the weak acid, and so even if that was not dilute, it would still be less corrosive. A concentrated solution of a strong acid is likely to be very corrosive. And that's the end of that presentation. Splendid.